Good afternoon, everyone, and welcome to the seventh session of Technic MasterTalks. Today to be dedicated to the Department of Nuclear Science and Engineering. I'm Miguel, a master student here at Technico, and I'll be the one moderating this talk. We'll have some time for your questions at the end, so until then, listen carefully about what Professor has to say. And talking about the professor, I would like to thank you for your invitation to accept our invitation to come here today with us. Professor is a researcher in the department, a researcher at CERN, administrator in the OECD Nuclear Agency, and a lot more. So thank you for coming, and with no further ado, please, Professor.
Thank you very much for this kind of introduction, short but efficient. And thank you very much, all of you, for being here today, okay? I'm obedient and I follow the script, which means they told me you have to think on an audience of students, okay? So my presentation is going to be directed mainly to students and, of course, addressing lots of activities, and we have lots of experts of what I'm going to say here in the audience today. So please feel free to interrupt at any moment, okay? So the title is Use of Ionizing Radiation, Nuclear Science and Society, and I'm going to flip a little bit. I'm going to speak firstly on myths and reality, and then to discuss shortly the risks and concentrate my presentation on the benefits of the use of ionizing radiation. You may notice that there is quotation marks in nuclear, and one of my main objectives is to simplify a little bit your view about what is nuclear and to correct some distorted ideas about nuclear. Okay, I will be spending some time on that. And of course, the other objective is to raise your awareness about all that is at stake when you discuss the use of ionizing radiation and nuclear in science and in society. So the outline of this, I will make a couple of dummy remarks and to entice you for the subjects that we'll be discussing later on in depth or in some depth. I will be addressing the myths, the reality, with facts and numbers about the use of radiation nuclear, the risks, the benefits, and one very important thing that is the other objective is that is most likely the second most important objective. I want you guys to get an idea of research topics that are at stake, okay? IST is a engineering, science, technology, and architecture school, and some of you will be looking at engineering, technology, and fundamental science aspects. So I will be discussing what happened at IST that is maybe not that well known. For instance, I will be discussing about knowledge, skills, competence. This applies to people, and then equipment, labs, and infrastructure. I'm not going to ask you questions right now, but I will ask you from time to time during my presentation. For instance, have you heard about what is CTN? Okay. Do you know the infrastructures and labs? Maybe. We are going to see this in the second part of the presentation. And then, of course, discuss about research topics that are undertaken by researchers. Some of them are in the audience, my colleagues at CTN and at C2TN, which is one of the research units, IPFN and others, and education and training. That is very, very important. We want to have students in our portfolio of master degree courses of the department, okay? So setting the scene, I'm going to make some dummy remarks. Some of you will find, oh, this is trivial. Sometimes you didn't look carefully at it. Look at this. It's quite an old report, but says basic things. I tell you, these are basic things. Is that the way how you react when you discuss about radiation is related to the information that we get at some moment in time about the biological effects of radiation, which means in cells and the aspects related to detrimental aspects eventually or potential to the human health. And very important, this is so important, attitudes that you take and change over time when you think about risk, in this case, risk of using or being exposed to ionizing radiation, okay? This is something which is trivial. Now, the underlying question is that you are always weighing what are the benefits and the risks and see if you can or not, or you should or not use ionizing radiation. And this is one of the important things about this. This is I would say, a very important. Think about this. These are the commonly accepted 3 steps on accepting or not some technology, some applications, not only in ionizing radiation, not only related to nuclear, but overall, is the perception of the risk, okay? First, you need to know that the risk exists. Then you need to evaluate, to assess what is important. Is high risk, low risk? I mean, how do you quantify these things? And then the last part is where things fail many times, and also whenever we discuss about radiation, is the communication of risk, okay? So this is something I told you. I would start by basic things, okay? But think about this. Ultimately, whenever you think whether or not you should proceed towards manipulating radiations or being exposed to radiation, is something that is related to what we assess as the risk of being exposed, which means the radiation effects. And therefore, it's a long and very complicated, is a fundamental science question, is how do you translate what happens from the moment where radiation produces at the physical level some effect in an atom or a molecule, down to the moment where sometimes years later you have a biological effect, okay? That translates by modification of the cell or DNA behavior, okay? So you see, we are basically dealing with the confluence of physics, chemistry, and biology, and most likely other sciences that I didn't list on this plot. So let's start by the myths. I would like to take the quotes after 2 or 3 slides of nuclear, okay? Well, these are trivial statements. The use of radiation has been distorted over time. There are decades of disinformation. Whenever you would go in the street, ask lay citizens what about radiation and what concepts you associate to radiation, they would tell you most likely about nuclear bombs and nuclear reactor accidents, and in some cases, at higher level, radiotoxicity of the fuel, the spent nuclear fuel in nuclear reactors, okay? These are some of them, but these are all catastrophic events or things that have some negative connotation, like radiotoxic, okay? Which is the toxicity due to radiation, like you have toxicity related to chemical behavior or to biological modifications, okay? And this is the yellow, and I crossed it. You should not accept this without properly thinking and discussing and getting information about that. Radiations are not inherently, just because they are radiations, detrimental to human health, okay? Let's see. What about nuclear? Nuclear or nuclear energy. Sometimes you, in the newspapers or in the media, you see nuclear, and we are discussing about something which, if you take it in the correct way, is going much beyond nuclear reactors, nuclear accidents, nuclear bombs, and so on. Nuclear energy. What is nuclear energy? I'm going to show in the next slide. Well, it's a trivial statement. It's energy released from the nucleus. It's carried by particles and radiation. I will not ask you what is the difference between particle and radiation, because that would take us somewhere else, is used in many peaceful applications and sectors. We're going to be seeing this, and strongly impacts society and lifestyle, okay? And whenever you speak about nuclear, you are also considering nuclear technology, nuclear techniques, nuclear engineering, whatever you want to put after the word nuclear, okay? Give you an example of nuclear energy, or several examples. Radioactive decay. You have a beta particle, you have an alpha particle, or in nuclear power reactors, you have a neutron that breaks a nucleus, and there is energy that is released, okay? In any of the three situations, there are many others, you have energy that is released to your system and that you are going to profit from if you are clever and do technology and applications based on that, okay? Energy. Let's now look at the reality, and I have to speed up a little bit. And the big message here is radiation sources and radioactive materials are all over, all over. Sometimes some of you do not have an idea that maybe close to you at this right moment, you have maybe a radiation or a radioactive source. And they are not harmful or dangerous, provided that you take care of handling them. I let you read this in medicine, environment, industry, energy, security, research, space, agriculture, lifetime, forensics, etc. Means many other applications. So they are basically all over. And radiotherapy, irradiation of food. I'm going to flash some applications, but there are many others. Radioisotope thermoelectric generators. Do you know that deep space exploration is only possible because you use radioactive sources? Plutonium, which is something that scares lots of people, among others, of course. Industrial radiography, blood irradiators in hospitals and so on. Oil well logging. Industrial applications with many gauges that you can use. Sometimes you are visiting an infrastructure, an industry, some facility, and you don't pay attention, but you'll find out sooner or later that there is a sign like this somewhere in a pipe or something like that, okay? Brachytherapy sources and civil engineering, construction works, and so on and so forth. And there is something which I was given in 2006, which means almost 20 years ago, but I think it's a very nice paradigm, okay? This is the triangular. How do you read? This looks like a pyramid, but it's not, okay? What this graph qualitatively tells you is that if you look at picocurie, which is very tiny radioactive source, tiny, I mean no hazard at all for you, you have virtually hundreds or more of millions in the planet Earth, okay, that are used, for instance, in some countries still as smoke detectors. So you can evaluate by thinking about smoke detectors, how many millions of smoke detectors are, and they use americium sources. And then if you go up in activity, which means if you have very strong here means with high activity, like for instance exists at CTN, one of them, you have a tiny number, okay? So the number gets scarcer and scarcer as you increase the activity, but you use for instance, for sterilization of medical devices, food, and so on and so forth, okay? And I mean, you go up the hill by looking at what happens in medicine, and of course that you read this vertically as the activity. But they are also all over in industry mainly. For instance, you can sum up and you have more or less 25,000 particle accelerators. We are excluding big accelerators like at CERN and other research labs. But just for industrial, I put here some quotation marks, ion implementation, and so on and so forth, irradiation of materials and so on. And then you have, for instance, worldwide, you have approximately 1,000 cyclotrons in operation these days. These are numbers from a very credible and serious report. It's cutting, I don't know why. And then, of course, I could not escape speaking about nuclear energy, nuclear reactors. That would not be serious from me, but that is important that you take the facts and the numbers and the issues and then you take your position. We have more or less, this is a round number, 440 nuclear power reactors. These guys are not operating, but to produce electricity, okay, that some of you indirectly or directly use, okay? And if you take the amount of electricity that is produced worldwide, 10% approximately is produced via nuclear, in nuclear reactors, okay? 53 reactors are still in construction, okay? You can read in newspapers that nuclear is going down, but that is not really. Outside the European Union and in other countries, you have the nuclear sector is expanding right now, in the United States, for instance, okay? And you have, of course, issues that you should never disconnect from, which is economics. The options that you take are many times driven by economy, financial aspects, the cost of producing the kilowatt hour in terms of electricity, but you have also safety issues, security issues. We're going to be seeing this a little bit, radioactive waste issues, proliferation issues, which are somehow related to security. And then you have also, and myself, I was a little bit scared the other day when I found out that this number is huge. You have approximately 220 research reactors. They are not producing electricity directly, most of them, in 50 countries. And they are using for research, production of medical and industrial isotopes, and for education and training. Like, for instance, in some countries, nuclear engineers are trained in nuclear reactors for research, okay? In the United States, it's very common. I mean, let's now look at applications, radionuclides. Okay. Look, one of the big applications is in the medical sectors. You have for imaging and for therapy, and you have radionuclides, which are gamma emitters, beta minus, beta plus, alpha emitters, and speaking now, Auger emitters. And you have also for non-medical applications. I let you find out the common ones like cobalt and cesium, but in the medical sector you have, look, this is currently used. This is the part of the plot, and then R&D, which means promising solutions for the coming year, okay? Again, coming from another report there. And then you look at this, and you see some of them are produced in cyclotrons, which are particle accelerators, and some of them are produced in reactors, and some of them can be produced in both, okay? Which means that one of the things that I'm not showing here, because I was trimming down my presentation because I had many more slides than I have today, is that it is not known, although it is not secret, then in 2009, there was a danger of disruption of providing technetium-99 to Europe and to big countries. Technetium-99 is used in nuclear medicine for different applications, medical applications, okay? Because some of the reactors that are producing, nuclear reactors that are producing this isotope were somehow going to kind of maintenance, some others getting old, and so on and so forth. So you see, the picture is more complicated, just say yes or no nuclear. I mean, you have to evaluate exactly what we are talking about in terms of the importance and the impact. December 2023, International Atomic Energy Agency, you can read this article, neutrons save lives. Neutrons sometimes considered these nasty particles, but they are used to produce radioisotopes in nuclear reactors, and these radioisotopes go to medical applications, for diagnostic therapy, or for industrial applications. And this is your lifestyle, okay? That's why I said lifestyle, because all these applications also are related to the way how you live, okay, in society. The risks, okay? So let's discuss the risks very quickly. Some of you have seen this. This is the tsunami flooding the Fukushima, and a few days later, whatever happened, I'm not going to discuss that. It's outside the scope of this presentation. And Chernobyl, where for approximately 10 days, you had a huge amount of radioactivity being released into the atmosphere. Okay, that is known. These are the risks, and we should not ignore them at all. You should really consider that they exist. Okay. The other risk is terrorism. Okay, and this is a nice thing because you take a conventional explosive, you attach to it a relatively tiny radioactive source. This is Times Square. You blow it, and with the explosion, you have aerosol fragments, radioactive materials that are scattered, and they will spread. This is a simulation. You can find this in the internet. And 30 minutes after, you have Manhattan that is somehow contaminated, quotation marks, with radioactivity. And it is estimated that the decontamination, besides being psychologically and sociologically very intense for the populations there, costs hundreds of billions of dollars. Okay, this is a huge thing, and it happens. I'm giving here Times Square, but it would be in any major capital or not even in a capital, in a big city. Okay, this is something that is very interesting. 2008. This is facilities, an institution that produces iodine 131 for medical applications, provides iodine to lots of hospitals in Europe. Okay, there was some, don't ask me exactly what happened, there was some problem, and there was an iodine release to the environment. Okay, the amounts here you see, it started here and then it slowed down, but the cumulative amount is the blue curve, and you see what happens around the facility, in 10 kilometers around the facility, people should not consume any goods and should stay at home, and so on and so forth. And these are monitoring staff looking at radioactivity in the ground and in other foodstuff. Okay, this happens. This happens. This is not fiction. This happens. The previous one is somehow fiction. This happens, or happened. It may happen sometime, but this is something which is saving lives. Okay, it's producing iodine 131. And you have many other that I will skip here. You go to the internet and you find them. The credible sources, of course, as usual, the International Atomic Energy Agency and other international agencies. So let's look now at the benefits, and I will concentrate now the last part of this first stage presentation by saying that the benefits clearly outweigh the risks. And one question that you may ask yourself is, how would you live without radiation? Maybe you didn't think about that. Some of you did, but think about that if you didn't. This is European Union, European Commission documents. You know that our population, if you include UK, is approximately 450 million inhabitants. And annually, 500 million procedures, radiological procedures, are undertaken in our space. Okay? Which means, in average, each one of us will make one radiological examination every year. Nuclear medicine, 10 million, and radiotherapy for cancer, 1.5 million treatment. Okay, this number scales to 4 billion worldwide. Okay, and it's increasing over time. I didn't include it there, but this is the importance that at the highest level, radiological and nuclear technologies play a crucial role in modern healthcare. Okay, and this is an action plan. It's called SAMIR, a strategic agenda for medical ionizing radiation applications. What are the objectives? Early diagnosis of disease, to move towards more personalized and precision medicine, increase the survival time of patients. And now you say, what are the, let's say, the vectors around which this action plan articulates? Look at this. Security of supply of medical radioisotopes. And these guys are produced, as I showed before, in research reactors, in cyclotrons, Then the quality and safety, that is more or less obvious. And then there is another component which is very important. If ever you consider doing or follow a medical career or track, is innovation in technology. It's going fast like hell, okay? Give you an example, proton therapy, okay? I will not comment on this, but this is for one of the manufacturers, but we are now getting to lower costs and more compact designs. It is told that the number is exploding worldwide. Conventional radiotherapy with many modalities. This one. Some of you do not know, but this is a C-arm that angulates around a guy that is going to be there dying because he had a cardiovascular episode. Okay? Right? And this saves every day. Right now in Lisbon or in Portugal, in worldwide, there are people being interventioned, like we say, using this technology. Okay? PET scans for brain scan, neuro diseases, cardiac functioning, and then an example of technology is a concept that is, instead of exposing just a tiny part of the patient's body to this scan, you do a whole body. Technology is also used for screening. This is one technology for mammography that is now picking up in Portugal also. By the way, it's recommended now. I'm not going into details, but we can discuss about that. But these days, people are recommended to do breast CT, to scan for potential lung disease using these technologies and so on and so forth. So we have technology being deployed for these three main, accurate and early diagnostic, personalized and accurate therapies and interventional procedures like I mentioned there. For instance, other thing, proton therapy compared to a modality of photon therapy, which is called VMAT, it's a modality. And then you can compare, because your ultimate objective is always to concentrate the dose that you deliver to the tumor, sparing the healthy tissues in the surrounding the tumor, okay? So this is medical physics, this is dosimetry, this is radiation protection. This is the example of something in which you think that this is not medical, this is physics, this is biology, this is medical, okay? You have a proton beam, and proton beams interact with the atoms of your body, you release neutrons, and then you have to evaluate the dose due to neutrons, okay? So these are complicated things, but are doable and are being done also in Portugal at IST. Then I'm going to speak about diagnostics in a flashy way, just saying that you have the radionuclide here. These are promising radionuclides that are already being used, gallium-68, yttrium-90, and so on. You use gamma emitters and beta plus emitters for diagnostic. This is a kind of a general rule, and the others for therapeutical uses, but you have to link this radionuclide to a vector that is carrying the radiation to the target, which is inside the tumor cell. And therefore, this is, let's say, the underlying philosophy in 10 seconds. Of course, it's very complicated from the point of view of preparing these substances. But what happens is that if you manage to have an electron entering let's say, the cell, it will travel a little bit, okay, and will deposit the energy and will kill the cancer cells. Whereas if it is an alpha particle, it will most likely deposit all its energy and will be very much effective in killing the cells, okay. What is at stake is science, technology, engineering, and then I call it life and health sciences, but you have to produce the radionuclides in nuclear reactors or cyclotrons. You have to prepare the radiopharmaceuticals whenever it is appropriate, chemistry and radiochemistry, and then you have to delve into biology and radiobiology as fields of research. to perform animal studies, clinic. This is, of course, an oversimplified picture. It's more complicated than that, okay? But just to tell you that nothing is separated. You have really the flow like that, and you have multiple steps. Then you have nuclear technologies and techniques applied to materials, environment, and else. You have here typical applications. Of course, that this list here is not exhaustive, but you have particle accelerators, nuclear reactors, radioactive sources, and materials. You have an example of nuclear techniques that I'm not going to enter into details. There are people in the audience that can. And this is a picture of a facility that exists at CTN that some of you may have visited. Okay, so that exists in IST. It's available for research and for education and training. Cultural heritage and forensics. Okay, you have here particle beam, and then you have an artifact or whatever, an object, and you are trying to discuss about dating, authenticity, provenance, and other things. And you use there for a picture. You can also use for forensics to determine is this authentic or not. And there are many other applications using techniques like what's called the nuclear microprobe, which is a tiny beam of protons, something which is called PIXE. And the other techniques are here. And you can also, by looking at the contents in, for instance, in this selected case here, silver and copper, you can get an idea of when was that object produced, okay? This is a very simplified. There are people in the audience that can ask, that you can ask much more complicated questions. I would like to visit space, okay? Space, I mean, I'm not going to discuss now. I mean, the cosmic radiation is characterized by HZE, which means IZ, I energy, which means very energetic ions, but it's not charge +1 or -1, is +4, +5, or -4, -5 sometimes, okay? And therefore, they're highly ionizing particles. And then there is this title, which is to 2014, is a little bit old, but tells you that astronauts going to Mars, for instance, the way back will be, I don't know, 3 years, maybe less, but they will be exposed to ionizing radiation. And whenever they get back to Earth, the risk of cancer has been dramatically increased, okay, by a factor of between 10 and whatever, because of being exposed to cosmic radiation, okay? There are other things about space that I don't have the time to mention. For the sake of time, I will skip this just to tell you that there are many what is called the spallation neutron sources, where you have a proton beam impinging on a target, then you produce neutrons, and you use this not for nuclear physics. Use this for research on materials, for energy purposes, for the proteins, biosciences, and so on and so forth. So this is done using nuclear physics and nuclear engineering and nuclear technology, but for the other sciences, okay? And you see, this is just pictures. If you go there, you can visit. This is a neutron line, and then here you'll have some experiment to measure the properties of the neutrons interacting. The other thing I mentioned is modeling and simulation. I mean, I will flash Monte Carlo modeling and simulation. These days, these systems are so complex, high energy, high intensity, high powers, and so on, that you have to simulate them before you implement them, before you project them up to the construction, okay? And here is something which is also very, I've been discussing about applications in medicine. This is, please concentrate here, 300 nanometers scale, okay? And this is how you model an alpha particle or a proton, okay? And each of these dots is one ionizing event, okay? And if you recall that the DNA structure is approximately 2 nanometers, it's a cylinder, if you describe it this way, you see that you have a tiny structure here where you may have lots of ionizing events happening, okay? So this is a very challenging thing. So the take-home message here, this is obvious. I mean, the use of ionizing radiation, nuclear energy impacts, benefits outweigh risks, and radiation research is needed in many different areas and addresses multidisciplinary, cross-cutting, and leading-edge topics, okay? please, this is a take-home message. Okay, so now the second part is what happens in Portugal. Okay, many of the things that I've been describing in the previous slides are also done, and in some cases in an innovative way, at IST, at CTN, at the department by the researchers. Okay, and so I'm going to tell you that this is a aerial view of CTN from Google Earth, and then you have this part here. That's where many things happen in terms of research, education, services, and so on. Okay, I will not discuss the details. We have here the vice president, and so let's come. This department of nuclear science and engineering is the researchers that work in this, members of this department. They work, most of them, not all, but most of them, in that campus. Okay, and so there is a kind of sometimes complicated relationship, but DECN is a department, is one of the 11 departments of IST, 11 so far, 10 up to a recent date. And then basically you have teaching, you have human resources, there are researchers, okay, and some professors, a couple of professors. Then you have the campus. The campus is the physical place where the infrastructures and laboratories, so-called laboratories for technological development, exist. And then you have research units, which are entities that gather research to undertake, researchers to undertake research. Okay, C2TN, I'm going to show that, the Institute of Plasma and Nuclear Fusion, and others, but I'm not going to spend too much time on that. The backgrounds and skills are listed there. I let you go. Basically, you have everything that you need to address multidisciplinary topics. And the areas, I will read them because it may be to stress. Also, nuclear science and technologies, I've been making the case for that. Radiation protection and safety, materials, life and health sciences, environment, geosciences, cultural heritage, plasma and fusion technologies, etc. Etc. means others, okay? So this is an old picture of C2TN, is Centro de Ciências e Tecnologias Nucleares. Tens of researchers, PhD and master students. And one thing that you can, one single word that you can use to describe this campus and the activities, the research activities, is uniqueness. It's a strong one, okay? Means that in Portugal, and in some cases at the international level, you have research that is done on that campus, and in some cases not anywhere else. Okay, did you know that? No. Okay, you have the main areas: advanced material science, earth systems and cultural heritage, and radiopharmaceutical sciences and health physics. I don't have the time to go through all of them, but these techniques that are in operation by the researchers have high sensitivity, high accuracy, and high degree of complementarity and synergism. I will skip some of them, but just to give you an idea, you have different facilities in support of the study of the electrical and magnetic characteristics of materials. You have other facilities that are used for synthesis, characterization, and preclinical evaluation. Here we are at a stage before radiopharmaceuticals and radionuclides are entering into clinical routine practice, but research is needed. You have also radiobiology, biochemical, chemical synthesis, and so on and so forth. Then you have laboratories in support of cultural heritage and environmental sciences, and other type of facilities, including an electron irradiator, a gamma irradiation source, other techniques and laboratories, clean room laboratories, and so on, accelerators in support of activities in this domain. Okay. Maybe I would let you go through this in 1 minute. These are the United Nations Sustainable Development Goals, and you see that I think this is a huge impact. if you have a campus, researchers, and facilities that address all these topics, it's huge. Cancer, so on. I mean, go through it. Air quality, radiological emergencies, advanced. I mean, go. Okay, I stopped for some seconds. Okay, you have the slides available, and you are addressing all these challenges here, okay, including climate and so on and so forth. The interaction of people working in this campus is enormous with research centers, universities, hospitals, and so on and so forth, not only at the research level, but also with companies, with municipalities, with museums, with professional associations, and so on and so forth, with military and so on, with schools that lots of students come to visit our campus at the secondary level of education. And this is one facility that is operated by IPFN that is also located in this campus. So I don't have the time, because otherwise I would ask you with a mandatory way of asking that you would summarize the take-home messages, but I don't have the time. So nuclear science and technologies exist in Portugal, exist at IST. They are led in some cases by researchers of IST and researchers of this department. They use unique infrastructures at the campus, okay, and equipment. And the DEC researchers have knowledge, skills, and competence in key scientific areas, cutting edge. And we have an education and training portfolio with 3 master degree courses, and soon 1 doctoral program. And what you get if you go there and work with people inside a team using the infrastructure and the equipment and labs is you not only look at the scientific aspects, but you also learn how to relate scientific and technology and engineering aspects with socioeconomic, ethical, and juridical aspects in some areas of activity. And that is good, because sometimes when we finish the courses at Technical, we are not aware of these relationships. So these are the 3 master courses: LED, Radiation Protection and Safety, Science and Technology for the Cultural Heritage, and the Medical Physics. And as I said that I was going to follow the script, I was told, do not go beyond this point, okay? And this is interaction that will happen after the session here is finished. Is this correct?
Yes.
Okay, so I stop here. I can show you, I am the coordinator of one of the masters. Isabel Diaz is the coordinator of the Master in Science and Technology, and José Marques is also in the audience, is the coordinator of the Master in Medical Physics, okay? And thank you very much for your time and for your attention.
So thank you, Professor, for the appealing presentation. I'm not from this area, but I listened carefully, and I have some questions. But before I do my own questions, I will ask you guys if you have any questions to the professor regarding the presentation, regarding maybe some of the masters, but you can also talk outside with in the atrium. So feel free to ask anything to Professor Pedro Vaz.
I can direct some of your questions to experts and to responsible people here in the audience, okay? And answer some of them, of course.
I have one. I have to, because of the mic.
Can I ask you to please identify yourself? What are you studying right now? And if ever, I know that's a successless question that I ask students. What do you think of doing in 1 year time, professionally wise, whenever you are finishing your master's course, okay? No, many times you don't know yet, and that is not natural. Okay, please.
Hello, I'm André Fuiciano. I'm studying engineering physics here at Technico, and I'm thinking about going to either medical physics or engineering, nuclear engineering for nuclear energy, for example. And I was wondering, what are the job opportunities in Portugal coming out of this area? If there are a lot of them, or it's mostly related to this one research facility, which is CTN.
Okay. I would say that as a student of IST, the job opportunities are always very high. That is a first level statement before entering into details. For instance, and then I'll give the floor to my other colleagues. If you finish this master's in radiation protection and safety, and we have 3 students, former students in the audience that finished the course, you can also go to research, okay, at the level of physics, chemistry, or biology in the medical area. That is one of the ones that you favor. I gave you several examples. In radiotherapy, in theragnostics, whatever. I mean, to produce radionuclides for applications in medicine. But you can also go for any other areas, including materials, earth sciences, and so on, environmental, cultural heritage, and so on and so forth. Every area that includes radiation. And in radiation protection and safety, you have typically hospitals, but you have companies which are service providers. We have examples here also. You have the regulatory authority, Agência Portuguesa do Ambiente. Sorry?
Other agencies also.
Coming soon, other agency besides that one. And you can do, for instance, I recall now one former student of this master's degree that is now working in the European Spallation Source in Lund in Sweden, okay? I have others that applied, I'm not sure if to CERN, but I mean, you have basically, and lots of things in companies, not necessarily to do research or fundamental research, but also applied things, and to do something that lots of students in physics engineering do, is consulting companies that are also a big employer in general, okay? But to tell you that overall, I think that we have here members of the management council. The employability at Técnico overall is close to 100%. Okay, after 6 months, that after finishing after you graduate as a master's. Did I answer your question?
Yes,
Partially.
you gave very a lot of examples.
So you get lots of jobs. Don't worry. offers. So you can select in a vast array, and we can have some people here corroborating that, okay, if needed. But then I would give the floor to my colleagues. For instance, Rosa, can you answer this question? If, for instance, a student enrolls into this master in science and technology for cultural education, which are the opportunities, job opportunities?
In this area, you can work in museums, for instance, or for the conservation and preservation of cultural heritage, or even in civil engineering, if you work with some buildings that are important patrimony. So it's another part of the research that we do.
And then, for the sake of completeness, we have this Masters in Medical Physics that will start next fall. And José Marques, what are the job opportunities for this young guy,
Well,
for instance?
with this master degree, we want to contribute to the training of medical physicists in Portugal. It's an area where there is a strong need of trained medical physicists. It's a very long process. It took some time until the new legislation came up. Now we are following the European model. So people are expected to have a first cycle in physics or with a lot of physics and mathematics, then a second cycle in medical physics, and then they will have training in a hospital for 4 years. And after this long training, they will be recognized as a medical physics expert under the European model from the European Commission.
I'm just going to give you an example of what does a medical physicist, and if I get there. For instance, this is the the treatment planning for some tumor irradiation, okay? And this is obtained by specialized software. But the software is specialized, but the people manipulating the software also have to have lots of knowledge about physics and mathematics and so on and so forth. And this is one of the things that, one of the many things that you can do in medical physics, okay? Many others.
Okay, perfect. So any other question? Okay, not maybe you or you. Can I give this slide first? Okay, so.
Hello, my name is Beatrice, and I wanted to know what are the points when you talked about the DNA and the image that and alpha. There were points in those lines. So,
Protons, oh yeah.
yes,
Are you speaking about this?
yes. There is points in between those lines. I just
No, these lines are just the way of the software processing. But each of these dots is an ionization taking place. Okay, what happens is the following: you have here a 0.7 MeV proton or a 20 MeV alpha, and then each time an ionization occurs, you spend a tiny fraction of energy, which is close to 30, 40 electron volt. So you see a particle with mega electron volt can ionize a lot, because each time it ionizes, it just spends 30 electron volt. So you have a huge density of points, means a huge density of ionizations happening when the particle crosses 300 nanometers. And if you take DNA, which would be a 4 nanometers, you see, if there is lots of ionization happening, you can produce what is called the strand breaks. You break the DNA structure, and this can be, is not, it can be the precursor event for cancer later on. You remember my first slide? It takes time to manifest. It will enter in cellular behavior and so on and so forth. I used to say to students that one of the most beautiful devices in the universe is the human body, because whenever it happens, in a huge fraction of the times, 99.999 whatever, repair mechanisms come and solve the problem. But sometimes it fails, the repair, and then you have cancer or other diseases, not only cancer. Yeah.
but like the ones in the middle, between proton and alpha.
These ones?
Yes.
No, these are particles that are produced during an ionization, and themselves they will ionize. But these are no longer the initial particle. Okay, these are electrons most likely. Okay, the so-called the delta electrons,
Okay.
low energy electrons. Okay,
Thank you.
but this is a very nice, a very challenging area of computation and of research. Okay, I could spend hours on that, but yeah.
Thank you.
Thank you. So now for you.
Hello, good afternoon. A question I have is about the handling of isotopes in terms of transportation, because they are produced in specialized facilities, but they have to be transported, and they have nefarious consequences if handled poorly. Are there special regulations, like collaborations with the police, for the transport from the production facilities to their, well, the places where they're going to be applied?
Yes, surely. I mean, the transport of radioactive materials has to follow strict rules that are imposed by the regulatory authorities. Okay. So in some cases, I give you just an example: brachytherapy. Sometimes you have a van that is transporting tens of thousands of tiny brachytherapy seeds. These sources that you are going to implant, for instance, in a prostate or whatever, in some organ. And one of the things that you don't want, in some cases, this is transported coming from Spain in a truck or in a van. You don't want to have a car accident with thousands of radioactive sources being dispersed in the ground, because then you have the problem that is a safety problem. That is, if you have 40,000 spread, the number now is indicative, and you go to the ground with specialized teams and you manage to collect 39,999. One is missing, and you don't sleep until you find the last one, okay? Because if you let it in nature, sometime later on, people can come and be exposed. These sources are normally tiny in terms of activity, but yes, to answer your question, there are very strict rules imposed internationally and standards for transporting these radioactive materials, okay?
Okay, I was thinking like the explosive industry has like collaborations in terms of even security, even the trucks that transport, for example, explosives, are tracked by the police. Are these ones also tracked in order to like accommodate, for example, terrorist attacks for those substances?
For this example I was given, I don't believe that police is following this, because this is happening many times during the week, okay? But of course that these trucks or these vans have to be properly handling the radioactive sources inside containers. They have to be signals that they are transporting radiation and so on and so forth, in such a way that, you know, like you see in the fuel trucks, normally you see all these symbols and these triangles and so on. This also happens coming to radiation, to the transport of radiation. Okay.
Okay. Thank you.
Thank you. I don't know if we have any more questions. You?
Thank you. So I have two questions. Well, the first one is there any innovation for nuclear energy trash? So, like, for example, in the nuclear.
Yes. Nuclear waste.
Yes. Is there any way that we can, like, for example, reuse or something?
Yes. How many minutes am I left? No, because during the past 15 years, I've been involved in European projects where this is addressed. You have basically two main categories of techniques, and we have also an expert in radioactive waste, which is in the audience, and I will ask her to complement my information. You have chemical methods that allow you to separate the spent fuel. Spent fuel is, and we have here a nuclear engineering guy, you insert into the reactor, I'm going to oversimplify now the thing. You insert, let's say, uranium, okay? And then by nuclear reactions induced by the neutrons in the core and by decays, you start with uranium and you produce other species like neptunium, plutonium, americium, curium, and so on, okay? And then you have chemical methods that allow you to separate some of these, say, waste in specialized facilities. It happens, for instance, in France and somewhere also in the United States, if I'm not absolutely wrong, and maybe in a couple of other countries. And then you have another solution that is called the transmutation. Transmutation means change the behavior of the species, okay? Which means you start with, for instance, plutonium, and you break, using neutrons, you break the plutonium in what is called the fission fragments that are smaller fragments than plutonium, and they are less radiotoxic. And that would lead us to the discussion about radiotoxicity reduction, okay? One thing that I must say before giving the floor to Isabel is that this is a very hot topic, and it's certainly one of the things or topics that is limiting the acceptability of the nuclear power, okay? But even today, I was reading in a newspaper, American newspaper, that despite several efforts, the United States, 42 years later than the initial plans, still do not have what is called a repository that Isabel can explain, and maybe somebody else, to collect this very high radiotoxicity nuclear waste, okay? But there are solutions, chemical solutions, already in operation, and non-chemical or non-directly chemical, but they are still on the phase of design, conceptual studies, okay? So right now what happens is that the spent nuclear fuel is stored, I don't have slides, in what we call the storage pools. It's really a pool where you put the spent fuel, you extract it from the nucleus after 2 or 3 years, you put it cooling in water. And some part of it is stored in canisters or in containers at the surface inside the nuclear power plant. Okay? These are the two. Isabel, do you want to comment? I didn't want to go to the technical terms.
It's not a matter of political decision, that's fine, but there's still quite a lot of science.
Science and technology, okay? By the way, there is connected to your question, there is a student here that just finished a master thesis on the design of a repository. Kill me if I like a cave underground where you store in concrete structures for shielding, for attenuate the radiation. You store them and you live there for hundreds or even thousands of years. Nobody accesses that without proper authorizations. And those are the solutions that exist so far. You just leave the nuclear decay law act by itself, which means radioactivity will vanish over time, but in some cases a long time, okay? Millions of years in some cases, okay?
And the next question is about astrophysics.
That is not my field.
It's not astrophysics,
Yeah.
sorry. But in the beginning, you talked about the plutonium and with
The Cassini.
no,
Plutônio.
não, a parte.
Diga em português.
Eu lembro da palavra em português.
Plutônio.
As coisas que andavam à volta da Terra.
Is the Cassini spacecraft, yeah.
Yes, and you talked about with satellites and plutonium, I think.
Yes.
Like, how is it connecting?
These are the so-called RTGs, the radio thermal generators. You have plutonium-238, it is one of the nuclides, and it emits alpha particles. And alpha particles, they have a characteristic is that they travel for tens of microns and they deposit its energy locally. And this energy shows up as a form of thermal energy that then you convert in other forms of energy, including electricity, to make the spacecraft continue and all the equipment also connected to a source of energy. You cannot connect it to the outlet, to a plug, okay? You have to live with this energy that is released, is released from the decay, nuclear decay, and then converted into electricity or other forms, okay? This is plutonium-238, by the way. It's these days, you are trying to produce them in specialized reactors, including in Russia, and all this situation in Ukraine did not help too much. But this is one of the hot topics. The Voyager 1 and 2, these guys that went to Saturn, also had nuclear propulsion. Nuclear propulsion is one of the sources for deep space exploration. That is well known. Without nuclear energy, these probes could not be there 20, 30 years later and still sending signals to Earth, okay?
And is there anything new that we can discover from space with using nuclear energy?
Jesus. Well, I wouldn't say using nuclear energy itself. But I will give you 2 or 3 examples of studies that are conducted or have been conducted by NASA and the European Space Agency. One of the topics is not directly related to nuclear energy, but is, for instance, how do you behave, your body, the motion of the organs and fluids, in the absence of gravity, so-called the microgravity. And you can say, okay, no problem. But for instance, how does the immune system behave when you are in space? Okay, this is a study by NASA. The other thing that, I'm not an expert on that, but there is a very famous study by NASA. It's called the twins study. And this became even more famous because they basically were identifying twins, 2 persons identical, and one of them would go to space and the other would not go to space. And one of these guys is called Scott Kelly. He's very famous because he's now a senator of the United States. And he has a twin brother. And this guy has spent 340 days in multiple missions in space. In several missions, but 340 days. And when they compare at the chromosome level, they found that the telomeres, which is the end part of the chromosome of the guy that had been in space, were different in dimension than the guy that did not go to space. Okay, the effect of vaccines in space. Okay, all of this is being conducted, is active as NASA and European Space Agency and many other topics related to human health. To your point on nuclear energy is basically radiobiology. How do you react if you are exposed to high energy radiation? What is high energy radiation? It's cosmic radiation. It's high energy, means high doses, or at least significant doses accumulated over time. Deep space means Mars, which is the closest, no, not the closest. It's 3 years, 1.5 and 1.5 to come. But the lunar missions that are now popping up, even because of commercial applications, there is also radiation-related aspects. What are the biological effects induced by cosmic radiation when you are outside the Earth and without the protection of our atmosphere? Because our atmosphere is a shield of radiation, okay? And you are above, and in the deep space, you don't have protection, okay? Materials, for instance, how can you make the materials for the spacecraft in such a way that if you have a manned mission, which means an individual inside, radiation most of it is absorbed. Nowadays is no questions because it's so high energy that if you have a very thick spaceship, it becomes so heavy that then you don't have radioactive sources enough to propel it, okay? So you see there is lots of different things to balance. Engineering, science, and technology, once again. Okay?
Thank you all. Unfortunately, we don't have any more time for questions, but I invite you all to come outside with us and for your students or professors to ask questions between each other. So this is the end of our master talk. I will invite you to the next one. It's about mathematics, the Department of Mathematics. So thank you, Professor Pedro Vaz, for coming and for accepting our invitation. And thank you, the audience, for being such a confidence and appealing audience. Thank you all.
Can I make the pitch?
Sure.
A very short one. Please, those of you that did not yet, shame on you, visit the campus, go there as soon as possible, talk with us and interact with the teams, ask for visiting if you need so, for clarification about research topics like the question that you have been asked, and look at our master's programs, okay? Enroll in one of the 3 masters, okay? Thank you.